All right, in this problem, we've got a parent function shown in black, and that's the sine function. So what we want to do is we want to transform that into the dotted line, the function shown in the dotted line. So let's go ahead and do that. Over on the side here, I just popped up the 5 things that you need in order to write the equations, or the functions, the transform functions. And so we're going to use these. We're going to kind of go step by step and find these from the graphs, and then figure out how and where to put those into the equation. So let's go ahead and get started. So amplitude is always the distance from the center line up to the max or down to the minimum. You can also find this by taking the maximum point and subtracting the minimum point and dividing it by 2, dividing that distance by 2. So our amplitude, it looks like it, if we just kind of take this point right here, there's our center line, and we go up to 5, our amplitude is going to be 5 in this case. The center line, I just said, is right here. It flows all throughout, cuts that, that wave or that function in half. So that center line is right at 0, which means we didn't move up or down. All right, so when we talk about what these two things are going to be the vertical changes or vertical transformations that happen to the function. So when I go to write my function, those two pieces are going to go right where that A, right there, and the K are in the equation. So my amplitude goes where the A is. That's going to tell me my vertical stretch. So my amplitude ends up being 5. And then my K tells me I'm not shifted up or down, so we just have a +0 at the end technically, but obviously we don't write that. So the next thing we're going to go after are the horizontal transformations that are occurring. First one is probably the easiest one, is the phase shift. So I want to find, we said this is a sine function, so I want to find where my sine function, quote unquote, starts, which is typically at the origin in the center of the function. So that's where my sine function typically starts. This one starts in the exact same spot, and so that means there is no phase shift. So the phase shift is usually seen on the inside here. That's the phase shift, x minus h. Remember, it's opposite of what you see. So if it's a phase shift right, it's going to be x minus something. If it's a phase shift left, it's going to be x plus something in there. But as we just said, there is no phase shift for this one, so we'll just see an x on the inside. Next thing we want to do is attack the period and the frequency. And what you see in the graph is the period. What you see in the equation is the frequency. And so we have to be able to kind of bounce between those two and convert between period and frequency freely. The way that we do that is that the period is equal to what the normal period is of the parent function, which is 2 pi, and we're going to divide it by whatever frequency we see, and vice versa. We can just kind of manipulate this equation to come up with this other equation if I want to convert the period to a frequency, and we would get the frequency is equal to 2 pi divided by whatever the period is. So this is the one that we're going to use because we're going to know the period and we're going to want to find the frequency. The frequency in this equation is b. And so we need to figure out what our period is. So what we're going to do is we're going to go up here. We're going to pick a point. And for this one, I'm just going to go with the initial point at the origin here that I've plotted. You can also pick a maximum and then go to the next maximum. You can pick a minimum and go to the next minimum. All of those are viable, but the key here is we want to track what the interval on the horizontal axis is for it to go through one cycle or one wave. So for this one in particular, one cycle, if it starts right here, it's going to climb up to its maximum, it's going to drop down to its minimum, and then it has to return to that same point on the graph. And at that point, it starts repeating itself, so we know it's completed one cycle. So I'm going to look at this one. One cycle goes from 0, this is 0, 0, up to pi 0. So the interval on which it completes one cycle is pi. That means my period is pi. So I'm going to take that and I'm going to plug it in here in order to find the frequency. The frequency is 2 pi divided by period that I just found. That tells me that the frequency is 2, which also means that within a normal 2 pi period, so from 0 up to 2 pi, up here, we're going to see 2 waves. This is the number of waves within a 2 pi period. All right, so we're just going to plop that into our equation. That goes in the b we said before, so I've got a 2x on the inside. This is still a sine function, and I've now completed my transform sine function. There's the full equation that accounts for all of the different transformations. So these next examples, we're going to take the exact same process, obviously different functions. So we've got to identify the particulars for each function, but that's the process. We look at these 5 things, and then we make sure that we incorporate them into the correct spot in the equation. So fix something real quick. We got to make sure we're in factored form up here. So let's go ahead and go through. We're going to go through a little quicker on these. So amplitude here goes from 5 down to -1. We chop that in half, and we get an amplitude of 3. You can also use the center line. The center line in this case is y equals 2. So from 2 up to 5 gives us an amplitude of 3 as well. So I've got the center line, I've got the amplitude, I've got these 2 parts or pieces of this equation. This is not a sine function. This is actually a cosine function. You can write it as either one, but we're going to write this one as a cosine function. And the reason we're going to is because it, quote unquote, starts, or on the axis, we're starting at the maximum. And that's what the parent cosine function does. So you can see here the parent function that's shown in the dark and the black starts at its maximum. That's what cosine does. It starts up at 1 and then continues through its cycle. So we'll use cosine in this particular case. Let's go and find the particulars for the rest of it. So we need the phase shift. So it's not shifted left or right, meaning that this initial point right here, the maximum, is not shifted over either way. And so we have no phase shift on this one. So all that means is on the inside in here, again, I'm not going to get an x minus h or an x plus h in there. And now we just have to account for the frequency. So let's check out the frequency. In order to do that, we've got to get the period. And in order to find the period, I'm going to go from my point. I'm going to go find that next maximum where it runs through one cycle. And I'm going to look at the interval on which that happens. So this one starts at 0 and it runs up to 3 pi here. And so my period is 3 pi. The interval on which one cycle, the interval on which it completes one full cycle is 3 pi. And so in order to find my frequency, I'm just going to take 2 pi and I'm going to divide it by the period that I found. That gives me 2/3. So in other words, I'm going to see 2/3 of a wave in a 2 pi period for this particular function. Plug that back up in here into the equation, and we've got our function, cosine function, with an amplitude of 3, a vertical shift of 2, and a frequency of 2/3. All right, let's check out this next one here. Again, we're going to run through our 5 characteristics and then just kind of plop those into the equation. So start with center line here and then amplitude. My center line on this one, this is a sine function, and it's, again, a sine function because the parent function that they've shown, we want to transform that. That parent function starts at 0, 0 at the origin, right in the middle of that wave, and then increases. So we're going to use a sine function to model this one. First thing is our center line is bumped up 2, which means our vertical shift, or that k value, is going to be +2. Next thing is the amplitude. So we measure from that center line up to the top of the wave or to the bottom of the wave because we have that symmetry. But that center line is going to have a vertical distance of 3 up to the max. And so we've got an amplitude of 3. So we plop those 2 vertical transformations into the equation. we get 3 times the sine of something. And then on the outside, it's a +2. So let's look at the phase shift. Again, this one is translated straight up, meaning I've got that center point still on the axis. We haven't shifted it left or right necessarily. And so I don't have any phase shift on this one. And then my period, I just need to follow this through one cycle. So it's going to come up, hit its max, come back down, hit its minimum, and then come back to that same exact point in the wave. And I've run through one full cycle, it looks like, in a period of 4. And so we now need to just convert that to frequency. So I take what my normal period is, which is 2 pi. I divide it by the period that I see in the graph, which is 4, and I get pi over 2. So there's my frequency. So in other words, I'm going to see pi over 2 waves, which is kind of weird to say, but it's about 3 point something over 2, which is about 1.5. You're going to see a little more than 1.5 waves in a normal 2 pi period. So that goes up into my equation. Looks like a pi over 2x on the inside, and there's my function, just accounting for those characteristics. All right, last one here, taking that same process. This one's a little trickier though, so let's go ahead and kind of dive in. So first and foremost, they want you to write it as a sine function because the original function in the black that they gave you is the parent sine function. And so there's a couple different things going on here. Number one, if we were given the option, it would make more sense to write this as a cosine function because I can use this as my kind of initial point. It started at the max, and that's what cosine does. So just something to think about if you're not given a parent function like that you have to work off of. This one would probably be a little bit easier to work with a cosine function. Okay, so let's go ahead and start with the sine function because that's what we need to do in this particular case. So we have to find our center line on this thing, and our center line is down here at y equals -1. That's going to split that wave in half. So it's shifted down 1 if it were a sine function. And actually for a cosine function as well. But the amplitude from there, we're going to go up 2 to hit the max. So we have to go up from the center line up 2 to hit our maximum. So that gives us an amplitude of 2. And now we've got to mess with the phase shift. So let's think about where sine usually starts. Usually it starts, and when I say starts, it's continuous. So it doesn't technically have a starting point. But if we look at the origin, that's usually kind of the first point that we work from on a sine function. So it usually passes through that origin. This one is bumped left 1 and also down 1. So we got the down 1 already with the center line, but the left 1 has to be incorporated into the phase shift. So the phase shift is left 1 unit. And the way that we express that is we go inside the parentheses, and everything on the inside of the parentheses is opposite. So we usually think of left as negative. In this case, it would be x plus 1. This would indicate a phase shift, left 1. Last thing that we have to do now then is we've got to account for the frequency, and we have to find the period first in order to do that. So I like to go kind of max to max. You can also go, for a sine function, you can go from that center starting point, cycle through one wave, go up and then down until you reach that center starting point. Again, that same point in the cycle. It looks like it goes from -1 to 3. And again, we can also confirm that if we just go max to max, we would go 0 to 4. So that would give us a period of 4 units. Let's go ahead and convert that. I want to find the frequency so that I can plop that into the equation. That's 2 pi divided by 4. That gives me a frequency of pi over 2. So I just plop that up into the equation up here, and we're good to go. And there's our sine function. So I mentioned before that we could also write this as a cosine function. If we wrote this as a cosine function, it would just look like this. We would still have the same amplitude. It would still have the same vertical shift, but our horizontal shift goes away. and the frequency also stays the same. So our cosine function looks like that.